Hello, I'm Zhongyan Zhao. I will introduce a new reinforcement learning framework for repetitive combinatorial optimization problems. In a combinatorial optimization problem, or COP, we have a bunch of discrete decision variables subject to relational constraint. The goal is to minimize the total cost. This type of problem is non-convex and often NP-hard. For example, with maximum weighted independent set problem, we're going to find a set of disconnected vertices such as red nodes that maximizes the total weight. While solving one problem is NP-hard, in practice, we often have to solve one instance at every time step. This type of problem appears in many applications such as communication networks, computer vision, distribution networks, cloud computing, and so on. The common truth is that network state of tomorrow depends on the decision made today. The cost vector changes rapidly compared to the topology, and our solution needs to adapt to changing topology and is subject to practical restrictions. In fact, our options are really limited by the practical restrictions. For example, in wireless link scheduling and computer vision, you have to solve one instance in tens of milliseconds before the next one comes. And this challenge cannot really be solved by using only a faster computer, because if you choose a centralized COP solver, then you first have to collect the full network state at the server. But because of the communication overhead, by the time you collect those network state already changes. So we have to rely on distributed COP solver in those cases. Can't we just use graph-layer networks? Well, the main problem of GNN is that they are bad at encoding the relational constraint. For example, if we want to find the maximum weighted independent set on this regular graph, where every node has the same weight, put it in a GN. Now every node has an identical input, so it will end up with identical prediction and identical decisions on every node, and that violates the constraint. Whereas conventional algorithm will always output a valid solution. What we propose is a hybrid pipeline, in which the GN learns the graph structure and the heuristic guarantees that the constraints are always followed. Both of them have distributed execution and can generalize to dynamic topology. Well, the only problem is that the heuristic is non-differentiable. So the main idea of this paper is to address this challenge through a twin network. The twin predicts the element-wise expected outcome of the heuristic. This is an easy task for GN because the expectations are continuous valued. Then we use the twin for backpropagation to train the actor GN. In this actor-critic framework, the critic is built on the fact that the system objective is a known linear combination of the output of the twin. Actually, we have two slightly different solutions for two scenarios. In the first one, where each instance can be optimized individually, the goal of the solution is to reduce the optimality gap at a minimum overhead. For the second one, the interstate dependency cannot be ignored. The goal is to achieve long-term system objective. Now let's look at the performance of our approach for the first scenario, closing the optimality gap. We use the three-layer GCN to enhance the baseline called LGS, which is a distributed heuristic for maximum weighted independent set problem. So our enhancement can close the optimality gap of the baseline by more than a third, and it can even slightly decrease the execution time of the baseline if we can reuse this enhancement for many instances. In training, our approach converges 2 to 3 times faster than the benchmark zero-solver optimization. We test our approach on another 3 NP-hard problems with similar pipelines. Of course, heuristic for each problem is different, and the approach can always close the optimality gap of the baseline slightly or substantially on different types of random graphs. For long-term goal seeking, we test our approach on delay-oriented link scheduling. Basically, our approach can achieve the same performance of an ad hoc training method, but is 5 times more efficient. To sum up, we address repetitive combinatorics under practical restrictions such as runtime and distributed execution, and we develop a general reinforcement learning framework that can either reduce the optimality gap or enable long-term goal seeking. It can be also extended beyond the combinatorics. Please check out the paper for more details. Thank you for watching.